Hey everyone, in the last video, I've shown you a program to compute the fourth factorial in using the analytical engine by Charles W. Babbage. However, a problem has been observed with that program. It's called fourth factorial anyway without loop. Okay. The problem with this program is it cannot be used to compute the factorial of any other value. It's fixed to compute the fourth factorial. For example, if you are going to compute for the fifth factorial, you have to change the value 4 to 5 in the first line, and then you are going to add two sets of steps that will compute for the final product, or rather for partial product, and the next multiplier. Subsequently, if you're going to compute for the sixth factorial, you have to add another two sets to compute for the partial product and the next multiplier. So imagine if you are going to compute for the 100 factorial, you'll have to write a very long code. So our problem will be to write a code which we do not have to change when the factorial value is changed. So we need to implement a function called repetition, such that the program itself repeats a number of times according to the specified number of factorials. Before we proceed, I'd like to introduce a special feature of the analytical engine, which is called the run-up lever. The run-up lever is a switch in the analytical engine that is automatically set or reset depending on the value of the egress axis or the output. During addition, if the sign of the first operand, which is in the ingress axis 1, is different from the sign of the result in the egress axis, then the run-up lever is set, which means it will have a value of 1. The same thing is true during subtraction, where when the sign of the first ingress axis is different from the result in the egress axis, the run-up lever is set. Multiplication does not affect the value of the egress axis. In division, when the quotient is larger than 50 digits or the divisor is 0, then the run-up lever is set. This is important because the run-up lever is used in performing or evaluating conditions, especially during repetition and branching. Now, let me proceed to the next type of cards which are used in repetition and also branching. They are called combinational cards. These are cards that are used for backing and advancing, which means moving backwards and moving forwards. They are called C cards or combinational cards. A combinational card is usually composed of 3 letters and 1 number. The first letter being C to stand for combinational or count. The second letter is either F or B. F stands for forward, which means skip forward or count forward. B stands for skip backward or move backward. The third letter indicates the type of movement. A plus means always advance or move back. CB plus means always move backwards, regardless of any condition. CF plus means move forward anyway, regardless of any condition. CF is a conditional movement. CF question mark means that we only move forward if the Mills run-up lever is set. Okay. CB question mark will only move backwards only if the run-up lever is set. If it's 0, it will just move on to the next command the normal way. So without further ado, let me show you the modification of the factorial program so that it will compute any factorial by using repetition. It's the same as the original program, except that uh, succeeding operations are repeated within a loop. The first few commands are the same. So when we say N004, we are assigning the variable 0 to a value 4, which is our next multiplier. Variable 1 is used as our uh, decrement, and variable 2 is our partial product, which is set to 1 initially. So that's just where the next, let's change that, it's 411. Okay. The next command is used to repeatedly compute for the partial product and the next multiplier. And then and after that, we are going to compute for check, or rather check the next multiplier if it's already a 1. We will stop multiplication if the next multiplier is already a 1. So our next multiplier is in 0, 0. Our partial product is in 1. That's the other way. And our decrement is in variable 2. The first step is to compute for the first partial product. So times L001, which is 4, and L00, which is L001, by the way, is 1, and L00 is 4. So 1 times 4 is 4. It will not affect the run-up lever. 1 times 4 is 4 without affecting the run-up lever. We'll just store the next partial product as 001. So this is now 4. And then we will compute for the next multiplier by doing a subtraction. First of L00, which is now currently 4, and L002, which is 1. 4 minus 1 is 3. So 3 is our next multiplier. And being a minus, it will affect the run-up lever. We have to emphasize that the run-up lever here is 0, although it's not used because there's no CF or CB. Okay, so the run-up lever is 0 and the value 3 is set to 0, 0. So our next multiplier is 3. Then we will check if our next multiplier is 1. We are going to do a minus of L00 with 2, which is 1, and L00 which is 3. 1 minus 3 is negative 2. Okay, so therefore the run-up lever is 1 because the sign of ingress is negative and the first argument is positive. Here comes our first CB. CB with a question mark is conditional, which means that it will only count backwards if the run-up lever is 1. Since it is 1, it will count backwards. Now the documentation of the analytical engine states that we start counting at the command right after the CB. So we'll do a count backwards 12. Now if you compare this with the actual code, there seems to be a change because the CF in that command is CF11. If you look at our reference, let's look at that now. It's here. The same program, which is in our reference in the internet, shows that it's CF11. It's here, rather CB11. It's because at this point it doesn't have the minus operation. It's not needed, although it's optional, because the analytical engine will perform the last operation that was used. In this case, if you ask what will be used by L2 and L0, it's a minus. In the program which I demonstrated, I indicated a minus so that it will be clear that a minus is done. Anyway, it's just for clarity purposes. So we'll do a CB question mark 12, which means we will go back 12 steps backwards. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we'll go back to the first multiplication. So this is now our second pass. We have pass number 2. So remember that the code repeats without having us to change the code. The next multiplier is 3. 4 is the partial product and 1 is the decrement. That's the last value. Okay, I'm writing the last value so that we don't have to scroll so much. Let's proceed to the second pass. We do a times of L001. L001 is 4, and L00, which is the next multiplier. Okay, 4 times 3 is 12. The run-up lever is not affected. We just store it to 001. So this is now 12, the next partial product. And then we compute for the next multiplier. The current multiplier, which is L00, is 3. We minus 1, so the next multiplier is a 2. And the current up lever is 0, although it's not used. But subtraction will set or reset the run-up lever, and else and S000 will store the next multiplier, which is 2. And then we'll check that multiplier if it's 1 again by doing a minus from L002, which is 1, and L00, which is 2 now, currently 2. So 1 minus 2 is negative 1. So there's a difference between the signs of the first input and the output. So this run-up lever is 1. And we have a CB12. We will do the CB because we have a run-up lever is of 1. And so we will repeat to the third pass, during which our next multiplier is 2, our partial product is 12, and our decrement is 1. 12, yes, that's correct. Let's move on. We are now on the third pass. Okay, we again compute the partial product with the times L001 is 12. Okay, L00 is 2. 12 times 2 is 24. The run-up lever is not affected, but we store the next partial product at 001, which becomes 24. Okay, S001, so this becomes 24. And then we'll compute for the next multiplier by doing a minus of L00, which is 2, and L002, which is 1. It's always 1. Take note, this is 2, and this is 1. So 2 minus 1 is a positive 1. So the egress axis is of the same sign of the first input, so the run-up lever is 0. It's not used because there's no CF or CB. We'll just store the next multiplier to be 00, which is 1. Minus L00. The next is a minus to check if the next multiplier is a 1. L002. So 2 is a 1 and 00 is a 1. 1 minus 1 is a 0. It's considered to be positive. The run-up lever is 0. So we have a CB here. This is the crucial point. Are we going to move backwards again or not? Obviously, we will not have to move because the run-up lever is 0. So we will now proceed the normal way, in which we are going to compute the final product by a times of L001, which is 24, and L00, which is 1. 24 times 1 is 24, and we will do a PBH. P means print it to the last card, B means ring the bell to call the attention of the operator, and H means halt. Take note that this can easily be changed to compute the factorial of any number. For example, we only have to change the first line without having to add or delete any lines of code. In the next video, I'm going to show a sample program in the analytical engine which does branching and control. So see you then, and thanks for watching.